talk, so I think we can probably start with an introduction. So we've got Endre Süli today with us from the University of Oxford. He's a professor in numerical analysis. I think you've been in Oxford since, it said 1985, isn't it, Endre?
Yeah, that's correct, yes.
Yeah, and professor since 1999, and a recent fellow of the Royal Society, I think, since 2021. Endre's research, as we're going to see today, recently has been focused on these kinetic models for polymers, but in the past he's also worked in a wide range of other topics such as solid mechanics, this idea that's quite popular in our group of implicitly defined constitutive models, done some work in fracture and discontinuities, but then a broad catalogue of books and papers on numerical methods such as adaptive algorithms for PDEs and multi-scale FEM methods. So yeah, really excited to hear what Endre is up to with this idea of well-posedness of these Navier-Stokes Fokker-Planck type systems. So yeah, I'll hand it over to you, Endre.
Thank you very much indeed, John. So thank you very much indeed for this kind invitation. It is International Women's Day today, 8th of March. So I decided to talk about a paper which is with one of my women doctoral students, Goslan Yahui, and it is hopefully also of interest to colleagues in Cardiff because it concerns non-Newtonian fluids. So there is also a numerical aspect to the whole thing of what I'm going to talk about, but I'm not going to touch on this today. The problem being that these Fokker-Planck equations that arise in these kinetic models of dilute polymeric fluids are very high dimensional partial differential equations. So the numerical solution of these equations is a real challenge. But today I'm going to talk about a non-numerical topic. It's about the derivation of these models. So in fact, what I'm going to tell you today has been motivated by a series of long discussions with Andrew Stewart, but ultimately the paper that emerged from this work is by Goslan and me. So it is her PhD thesis. So let me put up this picture. Let me try to explain what is happening. So we have polymer molecules, which are represented as a collection of beads linked with elastic springs in a moving fluid. So U here is the velocity of the fluid, and X here represents X, Y, and Z, the three spatial coordinates of the velocity field, and then we have time. There will be an equation which governs the velocity field, so that will be the Navier-Stokes equation, and then there will be another partial differential equation which governs the motion of this polymer chain, which is represented by the collection of these beads linked with these springs, and that will be the Fokker-Planck equation. So this is how this coupling of the Navier-Stokes equation with the Fokker-Planck equation arises. So let me just read out what is on the slide. A polymer molecule is modeled as a linear chain of massless beads, and you see that I have italicized the word massless because this is going to be important for what is going to happen later on in the talk. And so these massless beads are linked with elastic springs. So the beads which are contained in the fluid are subjected to Brownian noise. The assumption here is that the molecules of the surrounding fluid are bombarding in a random fashion these massless beads, and it is assumed that this randomness takes the form of Brownian noise. And everything takes place in a moving fluid. So you have this coupling of the Navier-Stokes equations with the Fokker-Planck system. So let me just say a few words about the notation, but this will come up later on also in the talk. Concerning the locations of the beads, what is usually done is you pick an arbitrary point, a fixed point in space. Here it's denoted by O, and with respect to that chosen point, you indicate the positions of the beads. So the jth bead here has position vector R sub j. So if you are in 2D, this is a two-component vector. If you are in 3D, this Rj is a three-component vector. And then you see another vector here, this qj, which is the orientation vector of the spring, which links the jth bead with the j plus first bead. So this q sub j vector is in fact the difference of the position vector of the j plus first bead, that's r sub j plus 1, and the position vector of the jth bead, that's r sub j. So qj is in fact rj plus 1 minus rj. So these R vectors is some sort of internal coordinate system, which at the moment is not linked in any way to the x, y, z coordinate system. So we'll have to worry about this. How exactly do these vectors Rj relate to the x, y, z variables? But we'll come to that point later. Incidentally, Tom, if there are any questions, or anybody out there, if you have questions, please feel to interrupt me at any point. So models of this kind go back quite a few years. An important article in this area is this one here by Hans Kramer. So this is the same Kramers whose name appears in WKB theory, Wenzel Kramer's Brillouin. He wrote this article first in Dutch because it was written in the time of the Nazi occupation of Holland, and apparently the scientists were not allowed to write the papers in German, so he published the paper in Dutch. Eventually it was translated into English a year or two later. Kramer's work relied on earlier work by Werner Kuhn and J.J. Hermans, who were statistical physicists also working in polymer chemistry. So there was also earlier work. So this was a very important paper which concerned models of this kind, which influenced subsequent work by Rouse and Sim. And there is a beautiful book by Bird, Curtis, Armstrong, and Hessinger, in fact, in 2 volumes. The second volume is the one that I'm referring to here, Dynamics of Polymeric Liquids, Kinetic Theory, published by Wiley in 1987, which discusses these kinetic models of dilute polymeric fluids. And on my bookshelf, in fact, here it is on my desk in front of me, is Tim's book with Rob Owens, Computational Rheology. So in chapter 11 of that book, you will find a very nice description of these models. If you have difficulties finding this book by Bird, Curtis, Armstrong, and Hessinger. Now, the point I would like to make is that these derivations that appear in the literature that I have cited are formal derivations. So they are mathematically correct, but they are not rigorous from the point of view of mathematical analysis. And in fact, to the best of my knowledge to date, there has been no rigorous derivation of the model from Brownian dynamics. And by rigorous, I mean, I hope I will demonstrate in the talk what I mean by rigorous. These derivations that appear in the literature that I have cited are based on arguments in statistical physics. Now, the lack of rigorous derivation of these models from Brownian dynamics resulted in a great deal of confusion in the PDE analysis literature concerning the precise form of the Navier-Stokes Fokker-Planck system. In some papers, you'll see the Fokker-Planck equation appears as a parabolic equation. In some other equations, it appears as a mixed parabolic-hyperbolic equation. It is also questionable that if you are assuming that the springs, which I have shown in this picture here, are Hookean springs, meaning that these are linear springs which in principle can extend out to infinity, how could it be that you have a bounded flow domain in which this configuration is placed, yet the springs which appear in the model can extend out to infinity? So there is somehow an inherent contradiction in the whole thing. So you will see these PDE analysis papers where the Navier-Stokes equation is posed on a bounded domain, but the Fokker-Planck system is posed on an unbounded domain to allow for the fact that the springs apparently can stretch out to infinity. So the main results here are the following. So I will give you a rigorous derivation of these Hookean bead spring models starting from Brownian dynamics. The results are in this paper, which you will find on arXiv. The paper is very long. I think it has something like 85 pages of analysis. So there's no way I will be able to tell you about all the details contained in this paper. I shall try to focus on the main results, but here is the summary of what comes out of this. So first of all, the first observation is, I think, an obvious one. If the flow domain is bounded, so this is the domain in which the fluid is contained, then the domain, this dj, is also bounded. So what is this domain d sub j? It's a j-fold Cartesian product of the orientation vectors, the domains in which the orientation vectors are contained. So going back again to my picture, these orientation vectors that I'm talking about are these qj vectors. So what I'm saying is that if the flow domain is bounded, then each of these qj vectors is contained in a domain D, which is bounded, and the collection of these vectors, and there are a total of j of them, given that there are j plus 1 springs, we have, j plus 1 beads, we have j springs, so there are j of these orientation vectors, and this is this configuration domain that I'm talking about here. So the configuration domain, which is the Cartesian product of the domains in which these vectors, the orientation vectors, are contained, is also bounded.
Endre, can I ask? Hi, Endre. Can I ask a question?
Yeah, please do. Yes.
I didn't understand. Maybe I missed this. What's the interaction between the fluid and the beads? I mean, why can't I just view the beads as I can just look at them in the frame of the fluid and they're just flowing around?
Yeah. So we'll come to that. That's an important question, in fact. So we will need to link somehow the fluid domain to these coordinates R, which I haven't yet done, but I'll do that. So the only assumption at the moment is you have some kind of coordinate system, which is some kind of internal coordinate system. At the moment, there is no connection between the XYZ domain and these R's.
Okay.
Is that okay? Was that the question?
Well, I mean, the question was more how do if the beads feed into the Navier-Stokes equation?
Yeah. Okay. So I'll say that.
Okay.
So that is the first observation. So is this okay? So there's this weird notation. This D domain is omega minus omega. So you might be wondering what on earth is omega minus omega. So this is just a notation for the algebraic difference of the set omega with itself. So this is the collection of all vectors of the form R minus R, because these orientation vectors are differences of vectors which are contained in omega. So this D domain is omega minus omega. Since omega is bounded, the D domain is bounded, so the configuration domain is also bounded. So the second result is the following, that before we take the small mass limit, remember I mentioned to you that it is assumed in these models that the beads are massless. They have no mass. But in order to set up the model, it is assumed at the start that they do have some small mass, and then we'll let this mass go to 0. So before taking the small mass limit, the Fokker-Planck equation is posed on a domain, which is this domain here. So the R vectors, so these are the position vectors, are contained in the j plus 1-fold Cartesian product of omega. The V's are velocities of the beads, and there are j plus 1 of these beads. Each vector V has, so this is the velocity vector of the jth bead, has d coordinates. So this vector is a really long vector which collects all the velocity vectors of all the beads, is contained in R j plus 1d, and this is the time interval in which t, the time, is contained. So this equation, before taking the small mass limit, is mixed parabolic hyperbolic. So it's parabolic with respect to certain variables, but hyperbolic with respect to some other variables, and I'll explain that also. But what is interesting is that after taking the small mass limit, so once you let the mass of the beads go to 0, because after all, you are assuming that the beads in the model, so this is a modeling assumption that you will find in all these books, these are massless beads. What happens is, as you let the masses of the beads go to 0, you end up with a Fokker-Planck equation, which is a different equation, but this limiting Fokker-Planck equation after taking the small mass limit is in fact fully parabolic. So it contains a diffusion term in all coordinate directions. And what is interesting about this is you will find this frequently mentioned in the book, and I think this is also mentioned in Tim's book, that you can derive the Oldroyd B model from the Fokker-Planck equation. So if the Fokker-Planck equation is fully parabolic and it contains diffusion in all coordinate directions, if you derive the Oldroyd B model, which is one of the sort of important models in this field, it's a fully macroscopic model. From this Fokker-Planck model, this Oldroyd B model will contain diffusion in the stress equation. And what is interesting about this is, so I'm sure Tim will be able to confirm this, if you do simulations with this Oldroyd B model without a diffusion term, you will frequently run into trouble with the numerical method. Numerical methods will just blow up. So what you find in the numerical literature, people frequently add in diffusion as a stabilizing mechanism into the Oldroyd B stress equation. So if you look at papers, for example, by Becca Thomases, who's at UC Davis, works on complex fluids, she has a whole series of papers where she puts in Oldroyd B into the Oldroyd B equation a diffusion term. So what I'm saying here is that in fact the diffusion term naturally arises in the Oldroyd B stress equation if you derive it from this Fokker-Planck equation, because the Fokker-Planck equation contains diffusion in all coordinate directions. And then finally, fourthly, there is a very nice result based on formal asymptotics by Schieber and Öttinger, who proved that in the small mass limit, something that they refer to as equilibration in momentum space takes place. So what this means is that once you pass to the small mass limit, the solution of the Fokker-Planck equation takes up a very particular factorized form. And in this factorized form, the equilibrium solution is one of the factors. And what comes out of this analysis that I will show you is that we can give a rigorous proof of this result by Schieber and Öttinger, which was based on some kind of formal argument based on formal asymptotics. So let me just pause for a second. Would you like to ask any questions? Is this okay? Does this make sense so far? Sorry, silence.
One question. So
yes.
Just jumped straight for the Fokker-Planck equation. I'm guessing I was expecting to see, some derivation showing that this had to be the description for this bead system. Are you just relying on the literature in the past that says, they're well described the Brownian motion by this type of equation, or is that something we're going to see come out, the Fokker-Planck?
Yes, so the Fokker-Planck equation will come out. So what I will state shortly is a system of stochastic differential equations, and then from Ito's lemma, Ito calculus, you get the Fokker-Planck equation.
Okay.
Right, so let me carry on. So once again, let me now be more precise about the formulation of the model. So here's again the same picture. We have these J+1 beads connected with elastic springs. I'm going to assume that these springs are Hookean springs, linear springs. You can make other assumptions on the springs. They don't have to be Hookean springs. You can assume various nonlinear spring relations. Here, I'm going to work with Hookean springs because from the point of view of analysis, this is precisely the situation that has caused most of the headache, the fact that you have these Hookean springs which can apparently stretch out to infinity. So the picture is exactly the same as before. We have these orientation vectors Q sub j, which is the orientation of the j bead, and Q sub j is Rj+1 minus Rj. U is the velocity field. So here's the notation. So I'm going to collect the position vectors of all the beads into a long vector, which I'm going to call R. So R1 is a column vector. I transpose it, I get a row vector, and I concatenate these row vectors, and then I transpose the whole thing so that in the end I get a column vector, which is a long column vector collecting all the coordinates of all the beads. So then we have the velocities of each of these beads. Again, there's J+1 position vectors. Again, these are pulled together into a long vector, which I denote by V. And then similarly for these orientation vectors Q sub j, okay, so Q sub 1 is a column vector, transpose it into a row vector, we concatenate these vectors and transpose, and we get a very tall column vector. So Q sub j is Rj plus 1 minus Rj. So now comes the point where we have to link somehow this internal coordinate system to the fluid coordinate system. Up to now, I haven't mentioned how these position vectors relate to the XYZ coordinate system. So what is assumed in the literature is that you take X, this position vector in which the velocity is evaluated, to be the center of mass of the configuration. So you take the arithmetic average of the R sub j's, and there's j plus 1 of them, and you declare that this is X, and this is where the velocity will be measured. Now, what is interesting about this observation, and I must say I didn't notice this before, and Endre was a person who pointed this out to me, these Rj vectors are random vectors because the positions of the beads are influenced by Brownian noise. So these Rj's are random variables. On the other hand, X is not a random variable, it's a coordinate in spatial coordinate in the fluid domain. So this arithmetic average of random variables is apparently equal to a deterministic quantity. So what this means is, from the point of view of stochastic analysis, you have a condition which relays these random variables in a particular way. So it turns out that this will be an important observation, and I must say I have not seen this observed anywhere in the literature, and it seems to me that part of the trouble that was encountered in the literature has to do with the fact that people have somehow missed this fact. So once again, these Rj's are random variables, and it is declared that the arithmetic average is X, the spatial coordinate. So this equality, in fact, acts as a condition on these random variables. So now we come to this hydrodynamic interaction. So we could take the Navier-Stokes equation. Here in this talk, for the sake of simplicity, instead of taking the full Navier-Stokes equation, I took the linearized Navier-Stokes equation. So instead of U, the velocity field, I inserted here a given sufficiently smooth, well, not that smooth actually, an L infinity function, so bounded in space and time, function B, which is assumed to be divergence free. So in the Navier-Stokes equation, you would have a U here, and that equation would be nonlinear. So I'm dealing with an equation which is called the Hookean system, so linearized Navier-Stokes equation. So the fluid domain here is assumed to be a bounded open domain. I'm going to assume that the domain is convex, and there's a technical reason why I'm assuming that the domain is convex. The reason being, I want to make sure that if I have two beads contained in the domain, and they are linked with a spring, then the spring is entirely contained in the fluid domain. So you can imagine some kind of non-convex domain where you have one bead over here, one bead over here, and then you connect them with the vector, and the vector somehow runs outside the domain. So I'm not saying that the equations or the model can't be used in numerical computations when this is the case, but the derivation is in the case when the domain is convex. The condition that it's a C2 domain, that it has a sufficiently smooth boundary, is just a technical condition. And there's another assumption here that the point 0 is contained in omega. This is just a technical condition. You can always shift the domain so that 0 is somewhere inside the domain. So this is the fluid equation, and the interaction between the Fokker-Planck equation and the fluid equation takes place through the presence of this guy K on the right-hand side. So over here on the left-hand side, remember U is a vector. So this is a vector equation. Pi is the pressure. So you have 2 or 3 equations in 2 or 3 dimensions. Over here on the right-hand side, you should therefore also have a 2 or 3 component vector. So this K is either 2 by 2 or a 3 by 3 matrix, depending on whether you are in 2D or 3D. And this K, which is called the polymeric extra stress tensor, so it's a matrix function which links the fluid equation to the Fokker-Planck equation. So K here will depend on the solution of the Fokker-Planck equation, and the Fokker-Planck equation will contain the velocity field U, which you have computed from the fluid equation. So there's a sort of a two-way interaction between the Navier-Stokes equation and the Fokker-Planck equation. So I'll come to the definition of this K in a moment. So what is this K? So again, this is something you will find in the literature. So it's called the Kramers-Kirkwood extra stress tensor. K at the point xt is defined by this expression. So let me try to explain what exactly this is. So you see this expectation here, and the way this formula is given in the literature is without the superscript x. The superscript x refers to conditional expectation, and this conditional expectation refers precisely to this point that I mentioned earlier, which was apparently missed in the literature, that there is a condition that relates the position vectors to your physical coordinate system. So this E here is not just a standard expectation, it's a conditional expectation. Lambda times Qj is the spring force in the jth spring. We are assuming a Hookean spring. So Qj is the extension of the spring. Lambda is a spring constant. So lambda times Qj is the force in the jth spring. And the formula that Kramers and Kirkwood use in order to compute the stress is this one here. The only modification I have made here is the fact that I inserted on the top of here the superscript x. So this expectation is not a standard expectation. It's going to be a conditional expectation because of this link to the fluid equation. This letter rho or var rho denotes the probability density function of the random variable associated with these random position vectors. So this is because the solution of the Fokker-Planck equation, this is this rho, features in K. Okay, so this function K is not something that is given to you. You can only specify what K is once you have solved the Fokker-Planck equation, whose solution rho is. And you can only solve the Fokker-Planck equation if you know the velocity field. So this is this two-way coupling that I mentioned earlier. So this E sub x denotes conditional expectation, and rho is the probability density function to be defined below as the solution of the Fokker-Planck equation. Is that okay so far? Do you have any questions at this point? Okay, so let me move on. So you have your velocity field u, and imagine you have evaluated, now this is the fluid velocity evaluated at all the positions of the beads, bearing in mind that the bead positions are random variables. So this u velocity will depend on rho because u is coming from solving this equation, and the right-hand side is k, depends on the probability density function. So u here, whatever you compute, will depend on this probability density function, which is contained in this k tensor on the right-hand side. So where does the Fokker-Planck equation come from? You have to write down the equations of motion for the beads. And what is written here is basically Newton's second law. Mass, this is this epsilon squared, times acceleration is equal to force. So what you need to do here is collect all the forces that act on the beads. First of all, you have a collection of these Hookean spring forces in this configuration. This L is a large matrix which describes the topology of this chain, the fact that you have a linear chain. You can think of other configurations. It doesn't have to be a simple linear chain, but here it is a linear chain. So you have this block tridiagonal matrix, huge one. The second force is Stokes' drag force, due to the fact that there is drag acting on each of the beads. And then you have Brownian force, Brownian noise acting on each of the beads. So this is a stochastic differential equation which describes the motion of the beads. So you have various constants here. The one that is going to be important for us is epsilon, because this is the mass of the beads, and eventually we'll let this epsilon go to 0. So you can take this second order stochastic differential equation and rewrite it as a first order system. So if I flip back, if you do this change of variables, you introduce the new variable v as epsilon times r dot, you define that as v. You can rewrite this system as this equation as a second order, the second order equation as a first order system. So here it is. So the thing to observe about this system now is that in the first equation, in this R dot equation, there is no noise, simply because of the nature of this substitution. And in the second equation, the V equation, there is noise. The consequence of this is that once you have applied Ito's lemma to derive the evolution equation, this will be the Fokker-Planck equation, coming from the system of stochastic differential equations, there will be no diffusion with respect to R, but there will be diffusion with respect to the V variable. So this is the reason why you end up, first of all, for finite mass epsilon with a Fokker-Planck equation, which has diffusion in the V direction. So it's going to be parabolic in certain directions, but it will be hyperbolic because there's no noise in other directions. So let's denote by rho the probability density function associated with this random variable. It's going to evolve in time. This is T. And so R is contained in this Cartesian product of the flow domains. The velocity V is contained again in the Cartesian product of Rj plus 1V. And T is contained in this time interval. And so we have a probability density function, which by definition is non-negative. So this will be the probability density function of this diffusion process RV. But what is interesting about this system of stochastic differential equations, if you look into what is sitting inside this U here, remember U is the velocity field that we derive. This comes from the fluid equation. And that depends because on the right-hand side of the fluid equation, we have this K, Kramer's tensor, which depends on the probability density function itself. You have a system of stochastic differential equations where in the system, you have the probability density function of the random process that you are trying to compute sitting inside the differential equation. So such stochastic differential equations are called McKean-Vlasov diffusion processes. So it's not a standard stochastic differential equation. The probability density function of the random variables is sitting inside the right-hand side of your stochastic differential equation. So the law of RV depends on rho itself through the function U. This is the velocity field, which is coming from the fluid equation, and it is therefore a McKean-Vlasov diffusion process.
Sorry, in the previous slide. So R, if you can go back to the previous slide.
Yeah.
R in the middle here in the definition of rho, R is in omega in this
J plus 1. Cartesian product, yes.
But what in the equation above guarantees that R stays in there?
Right. Okay. So we will put a boundary condition. When we write down the equation, there will be a boundary condition that I will give.
Okay.
So let me talk about this conditional expectation that is in the definition of this tensor K. So we define, first of all, the expectation. The expectation is the expectation of this random variable given by the standard formula where rho is the probability density function. So this is standard. And in fact, what you would find in books is this formula without a condition. But as I mentioned in our case, this should really be a conditional expectation. So how do you get this conditional expectation? And the way this works is as follows. So what we'll do is we shall perform a change of variables. And this change of variables is associated with the fact that I have defined X as the arithmetic average of the position vectors. So what I'm telling you is instead of working with the J plus 1, capital J plus 1 position vectors of the beads, I want to work with a different set of vectors. I want to work with the J orientation vectors and one more vector X, which is the arithmetic average of the R's. So this is a change of variables which we perform. We go from the R coordinate system to this XQ or QX coordinate system. And this is an affine change of variables. I haven't written down what it is. It's sort of a complicated change of variables. The point is that it has Jacobian equal to 1. You can verify this. So this R is now some affine function of Q and X. And instead of writing R here, we'll stick in this B of Q and X. So R will disappear, and we shall be working with the Q variables, which will be the orientation vectors, and the X variable, which is the flow variable. So then in terms of Q and X, if we sub in this B here, So the R disappears, and we have B of Q and X sitting inside here. We have the Q's as before, so this is the expectation. And now we have to put a condition on this. I want to talk about the conditional expectation. This is how I define this tensor K. The conditional expectation is the ratio of this expression above divided by the probability density function integrated. So this is the definition of conditional expectation. So this is going to be our definition of K. So here's the Fokker-Planck equation, and the derivation of the Fokker-Planck equation comes directly from ITER calculus. I'm not going to dwell on the details of this. This is completely standard. But what is to be noticed is, as I said earlier, you have a diffusion term, a second derivative, appearing in the V variables, because there is a noise in that V equation. After we rewrote the second order stochastic differential equation as a first order system, there is noise in the V direction and there is no noise in the R direction. So you don't have a second order derivative in the R direction. So this is some kind of transport term, drift term in the R direction. There's also drift term in the V direction. There's no diffusion in the R direction. So we have an initial condition, and now let me come to this boundary condition, because we enforce boundedness of the domain in which the position vectors are held. We need a boundary condition, and we simply assumed here, you can complicate this in many ways from the point of view of the analysis that is in the paper. What was simple is to assume a specular boundary condition, which simply means that every time a bead hits the boundary, it is reflected back. So it's like it acts as a mirror, comes in on a certain angle and it's reflected under the same angle. So it's a specular boundary condition. So this is this Vj star is the velocity, the outgoing velocity. Right, okay. So now I still have another 20 pages, and I'm not going to go into the details of these 20 pages. These 20 pages 10 pages are divided into 5 plus 5 pages. The first 5 pages are concerned with the proof of existence of solutions. The other 5 pages are concerned with the small mass limit, what happens as epsilon goes to 0. So the proof of the existence of solutions in the paper runs over 65 pages. So there's no way I can describe the details of this. So you will have to trust me that what I'm telling you is true, or you can go to the paper and check. So what is, just very quickly, we define what is called a Maxwellian. By this formula, it looks like a Gaussian, rescaled by this thermodynamic variable beta, which is the product of the Boltzmann constant and the temperature. So this is beta. And then instead of working with the probability density function, we work with these Hettich variables, which are the ratio of the probability density function and the Maxwellian. So this is useful at a certain point in the analysis, because certain parts of the operator using this notation can be rewritten in self-adjoint form, in a Sturm-Liouville form, and that's helpful in the analysis. So we introduce a function, which is this S log S function. So it has superlinear growth. It's a strictly convex function, so sometimes called entropy. F at 0 is equal to 1. F at 0 is F0 is 1, F at 1 is equal to 0. And then we make certain assumptions on the initial condition. The probability density function has to be an L1 function, has to integrate to 1, it has to be non-negative, and we make the assumption that m times f, this f function, applied to rho 0 hat is still in L1. So this condition is sometimes referred to as the initial condition having finite relative entropy. So then step 1 is the proof of existence of solutions to this problem for a finite epsilon. So we prove that there is a solution to this problem, the problem being this one here, the Ossin equation with this k epsilon tensor on the right-hand side. And I emphasize the presence of this epsilon because everything depends on the mass at this point. Divergence free velocity field, there's a 0 boundary condition on the wall. It is assumed that there is a certain initial condition that is satisfied, and k epsilon is this right-hand side here. then the probability density function, rather this rescaled probability density function, belongs to certain function spaces. We don't have to look into the details. Where these function spaces come from is from a certain energy inequality that I will show you in a second. So this is the weak formulation of the Fokker-Planck equation after testing with the test function integrating by parts. And it turns out that the solution of this Fokker-Planck equation has integral 1. And this is the energy inequality that is satisfied by the solution of the Fokker-Planck equation. So the only thing that is important about this energy inequality, and this will be important in a second when we send epsilon, the mass, to 0. So think about this energy inequality. Observe the fact that the right-hand side is independent of epsilon. This is a non-negative term. Multiply everything through by epsilon, so that or epsilon squared, that wipes out the epsilon square, and try to send epsilon squared to 0. So once again, imagine you have this inequality, which is true, multiply through by epsilon square and send epsilon squared to 0. So what will you observe? So clearly the right-hand side, as epsilon goes to 0, will go to 0 because of this epsilon square factor that you have multiplied by. This is a non-negative term, so you will drop it. So when you send epsilon to 0, and we'll do this rigorously in a second, what you will deduce is this object here, this sum, will have to tend to 0 as epsilon goes to 0. And what that means in terms is that because these are non-negative expressions, each of these guys will have to tend to 0. And what that means in turn is that in the limit, this derivative is 0. And what that means in turn is that these functions here that you have converged to as epsilon goes to 0 should become independent of Vj because the derivatives with respect to Vj are equal to 0. So this is basically the point of what is going to come next. The small mass limit. So let me just summarize this and I'm done. So from this energy inequality, we can pass, using this energy inequality, we can pass the limit. The reason we can pass the limit is we have certain bounds on the sequences of these functions. And once you have a bounded sequence in certain function spaces, you can use various weak compactness arguments to extract weakly converging subsequences. So these are the weak limits as the mass goes to 0. These functions converge to certain functions. The 0 here, subscript 0 here, is not the initial condition. It denotes the 0 mass limit of these objects in certain function spaces. So we also have boundedness of this k epsilon function precisely because of the fact that we have this nice ratio, and that comes from the fact that this k epsilon is a conditional expectation. You can show that this k epsilon is uniformly bounded, and that again is important because this bound, uniform bound, again implies certain weak convergence, weak star convergence of these k epsilon functions, and so forth. So from various energy inequalities, you deduce various convergence results as epsilon goes to 0. And this is the key inequality. This is the one that I mentioned before. If you multiply that inequality that I mentioned with epsilon square, and you let epsilon go to 0, what you find is that the limiting probability density function satisfies such an inequality. Now, clearly, this is a non-negative expression, and it has to be less than or equal than 0. So the only way this can happen is if the integrands, which are non-negative, are equal to 0. So what that means is that this rho hat function must only be a function of R and T. It cannot depend on the Vj's. So this limiting rho hat is only a function of R and T. But remember, these hatted variables are ratios of the original function and the Maxwellian. So what that means in the end is that the probability density function, because this rho hat was a rescaled probability density function divided by the Maxwellian, the probability density function itself is the product of this Maxwellian, which you have divided by when you define the hatted function, and this eta function. So the limiting probability density function is in this factorized form where M of V is this equilibrium Maxwellian times a function eta, which is independent of R and T. So this is now, in fact, the rigorous proof of this formal asymptotic result in Schieber and Öttinger that you have equilibration in momentum space. So this is precisely what they mean. You can pass to the limit also in the Gaussian equation using these weak convergence results. The most terrible bit of analysis that has to be dealt with is passage to the limit in K0. The problem being, remember, this K0 function, because of this conditional expectation, is a ratio. So it's a nonlinear function. It's a ratio of two objects. And all you have at this stage is weak convergence results. And weak convergence and nonlinear functions don't commute. So it is not easy to pass the limit in this K0. What is involved in passage to the limit in K0 is a use of a compensated compactness argument based on this Murat-Tartar diff-curl lemma. It's a long argument, but basically what comes out in the end is that you converge to what you expect that you will have converged to. I mean, if you just do things formally without rigor, you end up converging to this object here, where this eta function comes from this factorization of the probability density function, this rho zero, this eta. The only thing that needs to be done at this point is to decide what exactly is the equation satisfied by this function eta. I haven't said this, and this is now the interesting point. This eta is a solution of this equation, and look at this equation. This is a fully parabolic equation. So once you have converged to the small mass limit, the probability density function, this eta, solves this equation, and this is now fully parabolic equation. So it's not sort of a half-baked, little bit parabolic, little bit hyperbolic equation after you've passed to the small mass limit. This equation here is fully parabolic. You have an initial condition, you have certain boundary conditions. So finally, the only thing I'm almost at the end, the only thing I need to do, if you look at this equation is still written with respect to the Rj variables, whereas the fluid equation is written with respect to the x and q variables. So what I want to do is, given this Fokker-Planck equation, this fully parabolic equation, I want to remember this change of variables from the r variables to the xq variables. I go from the Rj variables to the xq variables, and this is what I end up with as a Fokker-Planck equation with respect to the orientation vectors and the x variable. And look, this is what is really interesting about this, highlighted in red here. You get a diffusion term in this equation, and this is the diffusion term, which is not normally present in what you find in the literature. So there is a diffusion term in the x variable. And why is there a diffusion term? Well, because if you look at this equation, there is a diffusion in all coordinate directions. So the fact that you have done an affine change of variables doesn't alter the fact that you have a diffusion in all coordinate directions. So it's a fully parabolic Fokker-Planck equation. You have a certain initial condition, and this M function is now again a Maxwellian. It's a slightly different Maxwellian. It's this guy here, but once again, as I emphasize, this really is a parabolic equation. And so from the point of view of macroscopic rheological models, such as Oldroyd B, the implication of this is that Oldroyd B, the stress evolution equation in Oldroyd B, is derived from this equation. The way it's derived from this equation is you multiply this equation with Q transpose, and you integrate over Q. And the outcome of that is that if you look at the stress evolution equation as derived from this Fokker-Planck equation, that stress evolution equation in the Oldroyd B model will also contain a diffusion term. So this is my final slide. So a simpler situation is if you imagine that your probability density function psi 0 is such that it's independent of x, or rather the integral with respect to q is independent of x, so maybe it's just a constant denoted by, you call your constant n to the -1. This number n is sometimes called a polymer density number, so this is a special case. So in this special case, what happens is instead of getting a ratio in this expectation, because the integral at the bottom in this conditional expectation is now constant in this special case, you end up with this formula for the stress tensor in this form. And this is the form that you will find in all books on the subject. I think this will be also in Tim's book. You will also find this formula in the Bird et al. Book that I mentioned before. So this comes out as a special case when this integral here is independent of x. So you don't get this ratio in the definition of this K0, this extra stress tensor. So this completes basically the derivation of the model that I wanted to tell you about. So there are some additional papers here. Once again, the details of what I told you about are contained in this paper with Goslan Yahui, and you can find it on archive. All the proofs with all the technical details are contained there.
I don't think we can see the last. You need to zoom out a bit. We don't see the bottom reference.
Zoom out now. Good question.
I don't think, or maybe it's just my problem, but I can't see the last reference.
Okay, so let's see if I escape. I don't know how.
Okay, I guess we can search it. But is it just my screen, or do other people not see the last reference? Oh, there we go. Okay.
So, okay, so it's McKean-Vlasov diffusion and the well-posedness of the Hookean bead-spring-chain model for dilute fluid, small mass limit, and the equilibration in momentum space. It's up on archive. And I'm done. Tom, thank you very much indeed. Guys, thank you very much for your attention.
Excellent. Thank you, Endre. Yeah, that was a really, really excellent talk. Now we'll take some questions from anyone. If you want to put your hands up in the chat, or just unmute yourselves. We got Tim up first.
Okay, so thank you, Endre. That was a very, very interesting talk. At the end, you mentioned that by taking the final Fokker-Planck equation, multiplying through by QQ and taking the average, you get, I would say, a modified Oldroyd B equation with stress diffusion. Have you derived that macroscopic equation?
So that is, okay, it's a very good question, Tim. In 2 dimensions, it is possible to rigorously derive, in 2 dimensions, I emphasize, it is possible to rigorously derive from that Fokker-Planck equation, the Oldroyd B stress equation with diffusion. So this is contained in one of my papers with John Barrett. Unfortunately, it is not the one that is cited on this page. It's a more recent paper. In 2D, we were able to do this. And what is interesting is that John Barrett had a paper with Sébastien Boyaval, where again in 2 space dimensions, they managed to prove the existence of solutions to this Oldroyd B model with stress diffusion. Without stress diffusion, there are no proofs of existence of solutions to Oldroyd B that are global in time. So it is not known that if you take out the stress diffusion term from the Oldroyd B model, even in 2D, it is not clear whether solutions will blow up. If you put in the stress diffusion term, in 2D, Barrett and Boyaval have proved that there is a global in time solution. And then similarly, John and I later proved that for this Hookean bead-spring model in 2D with this diffusion term in the Fokker-Planck equation, there is a global in time solution. In 3D, it is not known what happens. So the only thing we could prove in that same paper with John, that in 3D, we had problems passing to the limit in the Navier-Stokes equation. So we could only show, again, this has to do with the fact that we were working at the time on an unbounded domain. And there were problems with passing to the limit. We could not prove the existence of solutions. So we could only prove the existence of something that we call sub-solutions. So there was something like a defect measure, a non-negative random measure sitting on the right-hand side of the Navier-Stokes equation, which need not be identically 0. So we couldn't prove that the fluid equation was satisfied in 3D. And it's not clear whether, even if you put in stress diffusion, whether this is a well-posed model. So I don't know, Jim, have you done computations in 3D with Oldroyd B? Do you have any experience with?
No, mostly 2D or 2D axisymmetric. But you see the original model derived by Oldroyd, from continuum mechanics considerations, didn't have any stress diffusion, but
correct.
But people have been putting in stress diffusion for numerical stability reasons on an ad hoc basis. So it'd be nice, as a result of your theory now, to be able to go back to Hookean dumbbells, which using your derivation is not equivalent to the Oldroyd B continuum model. And see what model that you get.
That's interesting. Yeah, so if you look at Oldroyd's 1950 paper in the Proceedings of the Royal Society, indeed, as you say, there is no mention of any kind of stress diffusion in that paper. And I've seen these papers by Becca Thomas-Say and UC Davis, whom I mentioned. So she does put in stress diffusion, and there are other papers where the stress diffusion is put in an ad hoc basis in order to stabilize numerical methods. So all I can say that is, if you derive the Oldroyd B stress equation from this kinetic model, if you derive the Oldroyd B model, then the stress equation will contain diffusion.
Yes.
Now, you know, whether this is the stress equation that you should be using is another question.
Well, there are a whole array of models which even more difficult to analyze. You know, you've looked at linear springs, and you know there are yeah. Okay.
So this paper that I do mention here is on Feeney springs. So it turns out that, in fact, if you, instead of Hookean springs, you work with these nonlinear Feeney springs, the analysis is much easier. Mm-hmm. So then we were able to show existence of global in time weak solutions with these nonlinear springs. With these linear Hookean springs, the problem was that you have to work with these. In the papers that we did in the past, we always worked on unbounded domains, which probably wasn't the right thing based on what I told you today.
Thank you.
Thanks.
So, have we got anybody else with a question?
Maybe I'll just ask a quick question. So also about the existence of solutions. So is that, do you need to start by assuming that you know that there are solutions to the Navier-Stokes problem, or?
Okay, so it's a long story. So it goes as follows. So at the highest level, there is an iteration between the Fokker-Planck equation and the Navier-Stokes equation. So you give me a velocity field, which I take initially to be 0. I use that velocity field to show the existence of solutions to the Fokker-Planck equation. Then I take the solution of the Fokker-Planck equation, stick it into the right-hand side of the Navier-Stokes equation into this K tensor, and then I show that there is a solution to the Navier-Stokes equation. So you have a sequence which you generate by flipping back and forth between these two equations, and you have to show that this sequence converges. But before you do that, you have to look at individual equations. So you have to show that the Fokker-Planck equation for a given velocity also has a solution. So to do this, you give me a velocity field of a given regularity. I consider the Fokker-Planck equation. And the problem with the Fokker-Planck equation at that early stage, when epsilon is still finite, is that it's sort of this mixed beast, a little bit hyperbolic, a little bit elliptic. So it's a slightly non-standard equation. So the way the proof goes is you construct a Galerkin approximation using eigenfunctions of a certain operator. So it's a sort of an abstract Galerkin approximation, and you take a finite dimensional subspace spanned by these Galerkin basis functions. You approximate the Fokker-Planck equation, and you get a system of ordinary differential equations, and you show that these ordinary differential equations have local in time solutions. Then you show an energy inequality satisfied by the system of ordinary differential equations, and that energy inequality then guarantees that you have a global in time solution to that system. And then you pass the limit on the basis of, in this sequence of Galerkin basis functions. So that's one thing. And then you have to pass the limit in the fluid equation also. So the difficult part in dealing with that is this K tensor, which is this nonlinear function. It's a ratio of two objects, and you only have weak compactness at this point for the sequence of probability density functions. So what is used in that argument is the following. So you look at the Fokker-Planck equation, and this ugly part, which contains no diffusion, is chucked across to the right-hand side. What remains in the Fokker-Planck equation on the left-hand side is a hypoelliptic operator. And then you can use results by Diperna and Lyons, which they use for the Boltzmann equations. You have some sort of equiintegrability in uniform equiintegrability in L1 of these right-hand sides, from which you can extract strong convergence of the sequence of probability density functions. That then gives you almost everywhere convergence of the sequence of probability density functions. So you have some kind of pointwise convergence, and that you use in this ratio to pass the limit almost everywhere. And then there's sort of additional technical stuff to prove that you do converge on the right-hand side of the fluid equation to exactly what you expect. So that's roughly the idea of the existence proof.
I imagine, so the time of existence always should be the capital T. When you have a finite epsilon, should be T sub epsilon or something.
Right, okay.
So, and then you need to show that that's uniformly.
Yeah. Good question. So it turns out that because you have a uniform bound independent of epsilon, that existence time is also independent of epsilon.
Mm-hmm.
So if you look at these various energy inequalities, I don't know, I can go back to one of these. If you see an inequality, then stop me. This one here, you see. So this right-hand side is completely independent of epsilon. So for example, if you look at this term here, there is a uniform bound on this, completely independent of epsilon.
Mm-hmm. Okay.
So it's inequalities like this, which are the ones that guarantee global in time existence independent of epsilon. You're quite right. I mean, we would be in big trouble if the existence time shrank as epsilon went to 0. But that is thankfully not the case. I think I've overstayed my welcome. I see that it's 3 minutes past 3.
That's completely fine. But yeah, thanks again, Endre. That was really dynamic. And this will all be on the YouTube channel if anyone wants to look back over any details. But, yeah, thanks again. And yeah, we'll see everyone next week for the seminar then.
Thank you very much for having me. Very nice to see you. Thank you. Bye-bye.
Thank you, Endre.
Bye. Bye-bye.
Now.
Bye.
Bye.
Bye.